Hello everyone, I'm Mike, and this is the second video in my series on analyzing the P300 in the EEG data. So this video is about the classification of P300. Specifically, it's binary classification. So if there is of or if there is not. I will show a simple method to get you started, and then some pre-processing steps that you can take to improve the classifier. So we use the same dataset as in the previous video. So the auditory P300 task, you can repeat it on your own. You can use it in Colab or in your local Jupyter installation. And then when you're feeling confident, I invite you to use your own data and try to achieve the same or similar results. So let's get started. So as we did before, we can open our notebook with Jupyter or with Colab. So from my GitHub, you can click on the button Open in Colab. In that case, you also have to install the MNI library in the environment. And you have to make sure that you're loading the data from your Google Drive, so it's not going to be loaded automatically from the repository. I also simplified some of the functions of the previous notebook into a small pipeline, so we can just run the pre-processing, changing some parameters, and without running all of the code blocks again. So here I loaded my data, as you can see, and I still have to apply my yes. Perfect. So I create my MNE events in the data, and I can simplify the pre-processing. So in this case, I will just have a stronger filtering because we've seen during the analysis that we don't need much of delta and gamma waves anyways. And this is a full pre-processing pipeline. So after you run it, you get the filter data already. And if you want to visualize what's going on, I suggest you take the previous video and run each step separately. Then we also extract the epochs. In this case, I also made a choice. Each epoch is containing 350 data points. That's slightly more than 1 second because it also counts for a little time before the onset of the event. So by taking the last 200 data points, I'm sure that I'm including the P300 inside my epoch and excluding the rest. I still apply the baseline before doing this. So I still apply the baseline correction based on the data before the onset of the event, but then I will not use this data for the classification. And I will load them into my X and then the event labels into my Y, which are typical steps of machine learning setup. So you should be familiar with this if you've already done some machine learning. If you're not, these are data points and these are the targets, so the labels of each sample. So we have 90 samples. This is the shape. So 90 samples for 8 channels for 200 data points in each sample, and those are 90 labels. So we have to do some work with this data. It's an unbalanced problem. So first I will show you how to just prepare a classifier with the dataset as it is, and then we will see how to improve it by either oversampling or undersampling. So I usually pick a test size of 20% of the dataset for standard machine learning. For deep learning, if you have a lot of data, you can also pick a smaller amount. The train test split function in the Scikit library is perfect for this simple task. Basically, it's already preparing for you the dataset, giving you X train, X test, Y train, and Y test. So then you don't have to worry too much about this step. So it's a single function. And I also reshape my X. So I create XR and YR reshaped because the classifier I'm going to use, which is LDA, cannot take a multidimensional array as input. So this is my feature vector. I will put it again. Just to get you, just to give you very quick visual understanding of what I'm doing when I'm reshipping the data, I'm basically flattening all the channels into a single line. So now I use 4 channels, right? This is channel 1, channel 2, 3, 4, and we have 4 more. We basically flatten them and create a single feature array. This is pretty common for many machine learning models to do this, but it's also not very intuitive at first, especially if you don't visualize the data. It's hard to understand what has happened, where is that data point, like what's going on, right? So yeah, this is how it looks like for the model in human visualization. Now we are ready for our classification task. As I said, I decided to use LDA. It's not necessarily the best choice. So there are many models. P300 has been classified with neural networks, with super vector machines, even with transformers. So you need to make a choice and you need to make it like consciously. In this case, I pick LDA for 2 reasons. First, I don't have much data. I only have roughly 90 data points. And second, LDA has been used a lot for this type of task, so I know it's somehow going to work. And third, I also uh, evaluated this based on my data. So LDA assumes that your data follows more or less a normal distribution. So it should look like a bell curve when you plot it. So I plot my data. Those are the train and test set. And yeah, the distribution is not a clean Gaussian distribution, but you can see a bell shape. That means that this data can actually be discriminated successfully by LDA. Also, LDA also assumed that classes have the same covariance metrics. So in this case, it's important to rescale the data and minimize the outliers. So outliers are really skewing with LDA. It's important to keep that in mind when you do your analysis. So I apply a standard scaler. Here, it's really important that you train the scaler on the X-train dataset, and then you only transform X-test. Otherwise, if you apply the scaler on the entire feature set, you're basically going to leak information from the test to the train set. This is really bad for a machine learning study, because basically if you're leaking information from test to train, you're going to overfit on your data and you're going to have way better results. And sometimes you don't even realize. Sometimes you're just applying all the steps, following tutorials and methods. And this is kind of obvious for somebody who is in the field of machine learning has experience, but it's not very obvious for a beginner. So it can really ruin your entire analysis and weeks of work, and then you have to redo everything when you realize that there is a reason your classifier is very good on this data set and very bad on a similar one. That's the overfitting. So we run this, and for evaluating, we can use accuracy as well. Like this is the standard metric for evaluating how good is a classifier. So you may say, oh, 78%, it's actually not so bad, right? But then we have the F1 score, which takes into account false positive and false negatives, and that's 0, right? So we can visualize the effect of the F1 score with a confusion matrix. So that means that, yeah, how to read this matrix? It says that sometimes in this, at least with this test set, when we have a target, it classifies a non-target, and also it never classifies a target, like a true target, as a target. So it's actually a bad classifier. It's only classifying non-targets, right? But it might be just a bad division of the dataset. So we still want to do another level of validation. That's called cross-validation. So cross-validation means that we iteratively split a piece of the dataset that becomes the test set, and then each split of the dataset is sequentially used as test set. All the others are used as training set. Basically, you validate over each split of the dataset if your classifier is good or not. So when you do this, normally you still want to keep one part of your test data untouched. But in this case, I'm just showing how cross-validation works. So I didn't separate a test only dataset. So this cross-validation would not be very valid for the purpose of an online classifier, but for the purpose of showing how it works, then should be fine. So we run it. All right, so first let's go look at the metrics. We get 89 accuracy, which is better than the split we had before. And there is a variance of plus minus 9%. That means that sometimes we have 99% accuracy and sometimes we have 80% accuracy. So it's a pretty high variance for a model. And the F1 score is finally having a value different than 0, meaning that the model is learning something. Let's look at the confusion metrics. So, and I think this is the problem. Sometimes when we have a target, we predict a non-target, and sometimes when we have a non-target, we predict a target. So we do have some false positive and some false negatives, which is not ideal for a classifier. Let's see how we can improve from this. All right, we go back to this part where we are preparing the features. So as I mentioned before, this is an unbalanced dataset, meaning that we have a lot of epochs or samples that have a label of non-target and just a few that have a label of target. So that means that for the classifier, it's harder to recognize what is a target, right? Because it has literally seen less of this data. So how do we solve this? So there are several techniques. A simple one is resampling the dataset. So either oversampling, meaning that you are increasing one of the two classes, or undersampling, meaning that you are decreasing one of the two classes. So the thumb rule is that you want to use an oversampler when you have little data, and you want to use an undersampler when you have undersampler when you have a big dataset. And you can also choose the strategy. So knowing which strategy is going to be applied is important. So in this case, I have an oversampler that oversamples the minority class to an even level, and an undersampler that reduces the majority class, but keeping a ratio. So it's not 50-50%. So let's go first with the undersampler, which is not the ideal solution, but I still want to show you how it looks like. And we classify. So actually, we lose accuracy. So now it's a 70% accuracy, but we have increased the F1 score. That's still better than having high accuracy and low F1 score, because that means that, it's actually able to recognize some targets as targets, but we still do have these false positives and also some false negatives. So it's not an ideal classifier, but it's still better than having 90% accuracy and 0 F1 score. So we're still solving somehow the unbalance of the dataset. And then we try with the cross-validated. Okay, in the cross-validation, we also get another important information. We have increased the variance. So this is actually not good news, because an increased variance creates instability. So if you imagine to move this classifier into an application, a real-time application, a high variance is what causes the application to prompt wrong output more often, right? So meaning that the application is not reliable. There might be moments in which it's very precise and moments in which it's almost closer to random. So here we go even lower than 70% when in the worst case, right? So the variance is pretty high. Let's check the oversampler. Maybe that's the solution for our problem. So by uncommenting this line, I'm going to create an oversampler. So we only had about 43 data points. That's not much for a classification task with the undersampler. With the oversampler, as you can see, now we have 160. So it's a lot of data points. 128 are in the train, 32 are in the test set. And let's see if that already improves. All right, yes, I would say that we kept a very high accuracy, but the F1 score is amazingly high. And you can see it here. So when there is a target, there are no more false positives. Sometimes, um, sorry, false negatives. But sometimes when we have a non-target, we get a false positive. So that's actually normal for a BCI application. So a good BCI application should not lose any targets, so should not have any false negatives, right? Because that's basically that means losing information. And but it's likely that there will be some false positives. So it's not trivial to remove um, these false positives because they can also be caused by physiological reaction, meaning that maybe there is some actual P300 in the non-target data elicited by some stimulation that was not under control. And so it's very hard to make sure that there are none such of this data. It's not a discrete data, it's a time series with biological signal, and it's affected by many factors. So it would be very hard to get a F1 score of 1. But let's see the cross validation. All right, so I think I'm pretty happy with this. We have a 95% of accuracy. Variance is the lowest you obtain so far, or very close to maybe the non-oversampled example, but we have a F1 score that is very close to 1, right? So that means that we don't have any more false positives, sorry, false negatives again, but we do have some false positives, but way less than what we had before. I think this is totally acceptable for a real-time application. So just one more consideration on oversampling. When you're oversampling, you're also repeating parts of your data. That means that you may cause overfitting. So when you do oversample, it's always important to have a test set that is completely untouched by this operation, like a smaller part, because you may end up training a very good classifier that is actually not so good then when put into real-time application. So for this video, that's all. I hope you found the information insightful and that you can actually understand all the steps from data analysis to classification. I also invite you to change the classifier used for this task and to study how to prepare the data for the classifier. So, for example, support vector machine, or even a simple perceptron, a neural network that is not deep. If you want to use deep neural networks, you're going to need way more data than what I provide. So you can also do that. You can record your own data set and start from here and then apply a deep neural network. In that case, probably also you should use some library like PyTorch or TensorFlow, something more sophisticated than Scikit-learn. But if you're getting started, I think you have all the necessary here. I hope the video was clear enough and that the notebook can get you started on your project, on your research, or on your exam. If you like the video, please hit the like button. And if you want to see more, follow the page. In the next video, we're going to see how to clean the signal using independent component analysis. So thank you for watching.